let's get back into it. So we have our homework due tomorrow that is on the, I think it's deriving the equations for a beam using the variational approach that we discussed in class. The first problem that we went through, we used the variational approach where we derived the equation for stretching a beam. We then went on and solved that equation. You don't have to do that part. I just want you to find the differential equation and boundary condition or conditions that that would solve that problem. You don't have to go solve the ODE. That's due tomorrow at the end of the day. I feel like the last lecture, and I think what we're going to do today, it is not the most exciting in content. What I want to do is just ground it for you again, remind you what we did last class, and I feel like this is one of those ones where you really just need to practice something. And so what we're going to do in class today is I'm going to set up a couple of breakout rooms for the folks on Zoom, and then the folks in here can work together. I'm going to set up a problem, and we're going to solve the same problem twice using different guesses for our function and kind of talk about what's working and what's not. But before I do that, I just want to remind you what on earth it is we're doing. And we're still primarily kind of squeezing all the juice out of the lemon that is the principle of minimum potential energy, which is to say we have it. Let me share my screen. I'm going to be jumping between 3 screens today, so hopefully it's not dizzying. So briefly, and then I'll show you what I wanted to show you last class, but my computer died. What we're doing is we're saying we know how to write a potential, which is going to be a function of our strain energy, which is a function of displacement vectors. We'll, hold on, sorry. And maybe some loads. So our strain energy would be a function of our displacement vectors minus our work, which is a function of force times displacement vectors, maybe moments times angles. And at this point, there's kind of 2 approaches. The stuff that you're working on for your homework is we're going to say we can write down U and W. We don't know our displacement vector. So we have 2 options at this point. They both revolve around this one. On your homework, if we leave this as an unknown, then we take the first variation of our total potential energy, set it equal to 0, integrate by parts. That gets rid of all of our pesky derivatives of our variations. And then the end result is a differential equation for that unknown vector. Okay. So our first option is we say, I have no idea what my displacement vector is for my particular problem. We leave it as an unknown. We take the first variation of our total potential energy. We kind of turn the crank, do the variational calculus stuff that we practiced, and you arrive at a differential equation. Now, at this point, you can go further, solve, hopefully, if you can. Analytically, numerically, somehow solve this equation. And then you can plot your deformation, for instance, of your region. So these first three are part of the homework that's due tomorrow. You don't have to do the last part. Your second option is what we've been working on, which is to say, that we could guess such that our displacement vector has some constants a to the n times some function here. We will use Fourier series. Today we're going to use a polynomial series and a Fourier series. I'm going to kind of talk to you about the differences between these choices. We take the first variation of our strain energy and set that equal to the first variation of our work. This is the same as this. These are the same. Remember, if in the case of there's no loss of energy and there's no kinetic energy in the problem, then if there's just potential energy, strain energy, and work, then those two things are the same. You're just saying if delta U minus delta W is equal to 0, this is just saying we'll set them equal to each other. Room here. And then the third part is up until here, everything is exact. Up until here, everything is approximate. And then depending on how you end up solving the equation, you either get an exact solution or an approximate solution. There's a bunch of reasons why you might care about the difference between an exact solution and an approximate solution. One of those reasons is you need to be incredibly precise. You think about what NASA and JPL just did landing a rover on Mars. The precision needs to be incredibly close for various tolerance reasons. You should know whether or not you're making an approximation or whether or not you're solving something exactly. Another reason is pretty generic and straightforward and kind of sounds kind of boring, but say you want to solve a hard problem computationally, you have to validate or verify that that problem works on problems that we know the answer to. So what you would typically do is have a slate of problems that we can solve exactly, write your finite element code, and check to see if it works by testing it on the exact solutions that we know. And then you say, okay, I've got it working on all these exact solutions. Now I'm going to try it on this other problem that we don't know the answer to, and I'm going to trust that this is the right answer because we solved it on all these other problems. So our total potential energy, strain energy minus work. There's kind of two generic approaches. Your homework is let's get the exact differential equation, and then you can solve that if possible. And what we're doing right now with these approximate methods are guessing, and depending on how good our guess is and how many terms we keep, we will start to approach the exact answer. So last class, you peek through your notes. You might remember the first problem we did was we had a bar that was simply supported, and there was a moment, and we applied a moment at some point on there. I was hoping to show you something on my computer with it. My computer's here today, so let me do that now. I made this mathematical notebook unnecessarily complicated. I will try to walk through it. This is a problem from your old Mechanics of Materials textbook. It's the same problem we worked on. There's a bar, it's simply supported, there's a moment. It just so happens this one's an I-beam, so we have to know a particular value for I. This problem has an exact solution. That's really useful for us to get an understanding of what it is we're doing approximately. So the exact solution to this problem, if I was to say, what is the deflection of this curve? What is the deflection of this beam as I load it? The exact solution is here. And it's in two parts because you have that moment occurring at a point. So you solve from left to the point C, and then from C to the end. So there's two parts here. This top one is from the origin to C. It's telling you what the deflection of the curve is here. And the second one is from C to B. If you look through your notes, you'll see that we guessed that the shape might look like this. That's just the Fourier series. The notation is a little bit weird. Let me tell you what it is. So on the right-hand side, this should be pretty straightforward. Sum from n equals 1. Now, on our notebook, when we wrote stuff down, we wrote from n equals 1 to n equals infinity. You can't do that with these types of series on a computer because it's not going to converge to a particular value. You can't just sum to infinity. You have to tell it to sum number. How accurate? How many terms do you want to keep in your summation? So we're going to tell it to sum to some number, and this is our unknown. And then this is the sign series. If you look back in your notes, you'll see that we solved for an. We found the coefficients, and the coefficients look like this. Probably in here. Get this in our notes somewhere. Checking myself, yeah. So we did this. This is in your notes. So this would go into here, and this is our approximate solution. And then these are our exact solutions. Okay. So what I want to show you is what the exact solution looks like, and then what our approximate solution looks like as we take more and more terms. Let me scroll down. Okay. The red curve here is our exact solution. The blue curve is our approximate solution if we only keep one term. You can see that because it's got a 1 over here. Now I can slide this, and we can watch how our approximate solution does as we keep more and more terms. And you can see 2 terms, oops, sorry, 2 terms getting better. 2 curves didn't really change at all. 3 terms, better, 4, 5, and then around, say, 10 terms, they're pretty indistinguishable to me. You can get more detailed than that, and the plot above it is more detailed than that. The plot above it is saying, all right, let's just focus on what the deflection is where that moment is applied, and let's compare our approximate solution, which is the blue dashed curve, to what the true deflection is as a number, depending on how many terms we keep. So the x-axis is how many terms in your series did you keep. The y-axis is the deflection of the beam. And so you can see when you keep 1, it does pretty terrible. 2, I guess it's 3, 4, 5. You can see it kind of jumping up and down. And then you can see around here, around 10 terms, the error is incredibly small. But even if you're looking back around here around 3 terms, you know, this isn't too bad, or whatever this is, maybe it's 4. You know, we're off by microns in size. So it's kind of on you to figure out what level of precision you need for your measurements. But this is how the Fourier series method works. It says I've got a curve, I keep more and more terms, which is basically adding more and more of my sine components to it with different amplitudes. And you can see how that converges to the exact solution as we keep more terms. Questions about this? Stop sharing. We're really building up the tools for an incredibly powerful approximate method, which is used analytically and computationally, which is what's known as the Ritz method. And the Ritz method is incredibly powerful. It's basically what we're doing. It's just that you might have problems that involve lots of degrees of freedom. So we've only had one, right? We have a sine series with some unknown amplitude, a sub n. If you have plate problems, buckling problems, the Ritz method can be used to do linear, nonlinear, vibrational, buckling, static deformation, and all of these things. And it's just what we're doing right now. Like it's really nothing complicated. It's just saying, take the total potential energy, take derivatives of it with respect to all of the degrees of freedom, and set them equal to 0. And what we're going to talk about today is one of the powers of the Ritz method is that your guess doesn't have to be that good to still get sort of close to the right answer. And then you can improve on that by improving your guess. But the key thing is that I can give you a quantitative, like very clear description of what it means to have a good guess. And well, that's what we're going to go through today. In your textbook, so I would encourage you to read this. There we go. I would encourage you to read through, it's on your syllabus, but I'm kind of reiterating it here. You should read through chapters 10.10, 10.11. To be honest, all of chapter 10 is what we've been doing so far. So if you haven't been reading that, that can be really useful. And I'm going to assign fourth homework assignment. I'm trying to switch it up from the first homework assignment. My hope is that if I just assign you one problem, you'll spend a lot of time focusing on getting that done. I can give you more frequent, smaller homeworks as opposed to just having lots of busy work. This problem I'm assigning for the homework is not one that has an exact solution. So this is a nice example of when we actually need this. It's problem 10.48 in your textbook. For those of you working from an older edition of the textbook, the problem looks like this. I know this problem is in the older editions. I don't remember what the number is, but if you're looking at the older editions, you're looking for a problem near the end of chapter 10 that looks like two skinny beams and a thick beam. And I think there might be a force somewhere. Maybe it's here. Or maybe it's after two joints. I don't know. But it's this shape that you're looking for. So if you're using a different textbook, just look through chapter 10 for something that looks kind of like this. It's at the end. It's like one of the very last problems in the book. So the Ritz method, and oh, I should mention in your book, so this book, this problem, this method of approximating functions that we're working on is also commonly referred to as the Rayleigh-Ritz method. It's kind of a misnomer. Basically, Ritz wrote like this awesome, famous paper on it, and then Lord Rayleigh, who's a bigger name, like wrote him a letter a few years later. And was like, I've also used that, and then people started calling it the Rayleigh method. It's really doesn't matter. Anyway, it's the Ritz method. It's this thing here. It'll show up in your book as the Rayleigh-Ritz method, which is this chapter. But it's really just saying, you know how to write down total potential energy. You're going to make a guess. And then for however many different unknown coefficients you have in your system, you take derivatives, set them equal to 0. What I want to do today is have you get some practice on this. And the problem I'd like you to practice on is this one. It's a really simple one. And it's a simply supported beam. Under some distributed load Q, it's a uniform distributed load. And the first, we're going to solve this problem twice. The first time we're going to solve this problem, I'd like you to use the following guess for the shape, which is the deflection as a function of x will look like a1 times x minus times L minus x plus a2 which can be written as the sum from n equals 1 to infinity a sub n x to the n L minus x to the n. Where did this thing come from? It's a function that satisfies the kinematic constraints on this beam. The kinematic constraints on this beam are restrictions on displacement. So what are the key restrictions on displacement for a simply supported beam? It's that the beam cannot deflect at its ends. So if you plug in x is equal to 0, you should get the deflection of 0. And if you plug in x is equal to L, you should see that you get a deflection of 0. Pretty clearly. So that's how this thing was chosen. To satisfy the kinematic constraints. Okay. I found this to be fairly successful last semester. I hope it's fairly successful this time. I'm going to set up folks on the Zooms and some breakout rooms, and the folks in the classroom. You can work together here. If you have Mathematica, you can use that. I don't know if it'll make your life easier. It's pretty straightforward to do this on pen and paper. But I'll see if I can set up some breakout rooms here. I'm just doing this alphabetically, so I'm moving myself out. All right, there should be 3 rooms of 3 people. Please work together. This is the type of thing that just needs some practice, and this is I find to be the best way to get some practice. I will pop in and see if I can answer any questions you have. So I'll swing through each of the rooms in a few minutes. I'll let you get started first, and then I'll come and see if I can help. All right, good luck. You all can, if you want to work together, chat, or work on the board, or whatever's easier for you. But don't feel like you have to work solo just because you're. All right, we're back. Okay, so hopefully you are all, after we chatted, grab just the first term in this series. I hope that at this point in working on these types of problems, you know that the total potential energy is going to be the bending energy, because it's just bending minus the work. The bending energy, since we know something about the deflection, should be written in terms of the deflection. We know that the bending energy goes as the curvature squared, and curvature is approximately equal to the second derivative of deflection. So we get something like this. We have to take away the work. The work is going to be what? It's going to be the uniform distributed load to the force per unit length. That force per unit length is going to cause a deflection in the direction it's pointing. That deflection is going to be W of X. So force per unit length Q times W of X gives you a force. You're integrating a force over a length. That's going to give you a force times a length, which is energy. So that's the work. The nice thing about these polynomial functions is if you're just keeping one working terms, the derivative is not that painful. So you should have gotten something like 0 to L of pi over 2 times -2 A1. This should come from the second derivative term of your deflection. And then you don't have to do anything for your work. It's just going to be A1 Q X times L minus X. You can calculate this integral, polynomial, you know how to do that. You can, it's a definite integral, we're going from 0 to L. So you should be able to integrate and get your total potential energy looks something like 2EI A1 squared L minus AIQ L cubed over 6. The Rayleigh-Ritz method tells us we need to do this. If we had kept 2 terms, we need to do this twice, once for each of the terms, 3 terms, so on and so forth. That's all this is telling us, that for each term, we're going to have a coefficient. We should be able to minimize the total potential energy for each individual coefficient. So if you got this far, hopefully you found that the partial derivative of total potential energy with respect to A1 is just 4EI L times A1 minus Q L cubed over 6. We know that that should equal 0. And that is because of this. We can here solve for A1, and your first constant should be QL, oops, that's a squared, QL squared over 24 EI. And if you recall, this is the only thing we don't know about our guess. So now we're good. Now we can plot it. Instead, what I asked you to do is to say, we're going to compare this with a different answer. And the simplest way to compare something like this is figure out where the maximum deflection would be. This thing's going to be symmetric. It's going to bend like a parabola. So the maximum deflection should be in the center. So let's use the maximum deflection as our way to compare how good our answer is. So to find the maximum deflection, we insert this back into W, such that W of X should equal QL squared over 24 EI times X times L minus X. That's our answer. And then I asked you for W at L over 2, which is the W max, which should equal Q times L to the 4th or 96 EI. In the real world, you'll have to do a problem like this and you'll be like, all right, that's an answer. Like hopefully you have something to compare it to. Maybe you have an exact answer. Maybe you have a simulation. Maybe you have a structure that you built and you're loading it. You're trying to see how your experiments match your theory. Or maybe you have none of those things and you just have to say, well, I wonder how good of a guess I made. What if I try a different guess? At this point, you could go to your second term, third term, do this again. The nice thing is this is iterative. So what you can do is you can calculate the first term and then go back to your total potential energy, add in the second term. Now remember, you'll still only have one unknown. You'll only not know A2 at that point. You'll know A1. You can calculate through, solve for A2, and then you can iterate and go back to A3. These types of things are really easy to implement in like something like MATLAB or Mathematica, where you're basically kind of running through a for loop and you're using the solution to iteratively solve for the next one. What we're going to do is take a break, and I'm going to set up a second guess. Have you do this again, compare the answers, and then I'm going to ask you all to try to see if you can figure out which of these guesses you think makes more sense and why. So let's take a break until like 10:08. And then I'll send you a new guest and I'll send you off into breakout rooms to work on the same exact problem again, just with a different guess. All right. Get back to it. All right, we have an answer. We don't know if it's a good answer. We're going to try a different guess, try the same approach, see how we do. Same problem, everything's the same, except what I'd like you to do is use a Fourier series. And so let's take our guess this time. W of x is equal to the sum from n equals 1 to infinity of a sub n with the sine of n pi x over L. And just for the sake of making the work not awful and also comparing apples to apples, let's just look at A1 sine pi x over L. So just that first term in this case. I'll point out again that plug in W at 0 and W at L. This guess also satisfies the kinematic boundary condition. All right, I'm going to send you back to the same breakout rooms you were just in. We're going to solve again. What I'd like you to do is find W max. So that means put this into your total potential energy, minimize total potential energy with respect to A1, solve for, put that back in to get W, and then use that to get W max at L over 2. And the last thing I will ask you to do is you're going to get two answers that are sort of similar, but a little different. I would like you to try to think about and make a guess as to which one is more accurate, and then why. How are we doing over here? This is my guide to figure out where my regions are likely to be done. Yeah, they won? Anyone?
So,
What'd you get for a W max?
4Q 4 over pi to the 50 I.
4 over pi to the 5th. You got 8 over pi to the
Well,
4th.
with the other, with like A, Q, L.
It's like 1 over 76.
1 over 76-ish?
Roughly.
Yeah. Okay. Alright. Yeah, okay. It should be like 4 over, sorry, 1 over 76.5 or something.
Yeah, yeah.
Okay. All right, we're back. All right, what did folks get for A1 in with using this guess? The procedure is the same. Insert W into this. Ah, sweet. A1, perfect. So we got 4, pi to the 5th. Writing. Thanks, Megan. 4 pi to the 5th. L to the 4. Q over EI. And if you insert that into W of X, um, 4 times sine pi x over L. At this point, you can plot your shape and compare it with the other functions. You can kind of compare these two. A more direct comparison is to check what's happening at the max deflection. So at the max deflection, which is at L over 2, I'm going to approximate 4 over pi to the 5th so we get some sort of number to work with. And so we get here 1 over 76.5 UL to the 4th. I know some folks here got that. I'm hoping others in the other two breakout rooms got something, well, hopefully the exact same thing as this. And so your first takeaways should be, hey, look, this is all the same. That's encouraging. I must have done something right. Your second takeaway should be, these are different. What do I believe and why? So what do you think? Any guesses? Guess, a fine guess. A meta guess.
Are we guessing which one's more accurate or why necessarily just why they're different?
I think those two things are related. So one of these is more accurate, and the reason it's more accurate will explain why they're different. I can't think of a hint to give you that won't give the answer away. So I'm trying, but
It might depend on whether the shape of the beam in the actual analytics function approaches a sine wave as opposed to a parabola.
yeah, so the comment here is kind of like, does the analytical solution approach a sine wave or approach a parabola? And maybe that would guide our way to determine if which one's correct or not. That's true, but hard to use in practice because it's not reasonable that you be able to look at something and know where it's tending towards. There is something you can look at here that would allow you to make this judgment in a pretty precise way. All right, I will give you the hint that will give it away. Are these the only boundary conditions that this beam needs to satisfy? To remind you, the Euler-Bernoulli beam equation is that. So if you want the exact solution, you can just straightforwardly solve this problem. That's an ordinary differential equation. What order is that differential equation? It's fourth order. How many boundary conditions have we talked about? 2. You need 4 boundary conditions to solve a fourth order ordinary differential equation. What are the other 2 boundary conditions?
The curvature at each end has to be 0.
Exactly. The curvature at each end has to be 0. And the curvature you might remember that EI times the curvature is equal to the moment is EI of the second derivative approximately equal to the moment. So the guess that came from the audience here was that the curvature has to be 0. Why is the curvature has to be 0? It has to be 0 because of this boundary condition. Because there's no moment acting on the edges of those beams. This beam is simply supported. There's no torque or couple acting on the end. Because this yellow thing here is 0, and because these things here cannot be 0, this has to be 0. At the edges of the beam. Is it? You calculated the second derivative for the polynomial case. You got it was equal to negative 2a. X does not appear in that second derivative. X doesn't appear in that second derivative, which means you can't say that the second derivative of w will be 0 at each end. Now check the bottom one. Bottom one is sine of x over L. First derivative of sine is cosine. Second derivative of sine goes back to sine. Sine at 0 and sine at 1 is exactly equal to 0. The second one matches both the kinematic boundary conditions and the natural boundary conditions. The natural ones have to do with derivatives of our displacement. They match the ones that have to do with curvature. The exact answer to this problem, which is found by solving the equation I boxed in black up there, is W max equals QL to the 4th, 76.8 EI. The one that matches all the boundary conditions came closer. If you keep more terms, it will converge on the correct solution. The one that doesn't match all the boundary conditions is not guaranteed to converge to the right answer if you keep more terms. But it's not that bad. I popped into one breakout room and there was like, how do we do derivatives and then integrate over sine and cosine functions? The polynomial one's pretty straightforward. We know how to do that type of math by now. It got us close, but not quite. But the key thing is you can kind of painstakingly go through and keep as many terms as possible, and you're not guaranteed to converge to the right solution. It'll converge to something, but you're not guaranteed to converge to the right solution. If you match all the boundary conditions in your problem with your guess, you will converge to the correct answer, the exact answer, the more terms you keep. So it's a trade-off. The math is a little bit harder. Sometimes you might not be able to guess a function that matches all the boundary conditions. And so in that case, you don't just quit. You can just say, well, I know that I'm not going to have the exact answer. I'm going to have some error here that will be larger than if I had a better guess. But it's still an answer. So sometimes guessing a function that matches all your boundary conditions is not that bad. In this case, this is not hard. It's a Fourier series. Sometimes it's really hard. Plates, shells, you have to use a lot more complex functions. as your guesses. They're not just simply sine functions, they're gonna be sines mapped onto some crazy shape. So the takeaway I want you to have from this is that if your guess matches all the boundary conditions, your approximate solution will converge to the exact solution if you keep a lot of terms. If your guess doesn't match all the boundary conditions, you'll come close, but you're not guaranteed to converge on the right answer. I keep separating kinematic and natural boundary conditions. Kinematic are restrictions on displacement. Natural boundary conditions have to do with derivatives of displacements. They usually have to do with forces and moments. For any of these approximate methods to work, this is a really key point. For any of these approximate methods to work, you have to pick a function that satisfies the kinematic boundary conditions. I'll say that again. For any of these approximate methods to work, you have to pick a function that satisfies the kinematic boundary conditions. It must match. So if there's going to be no displacement at a wall, your guess better be 0 where that wall is. You can use these approximate methods if your guess doesn't match the natural boundary conditions. You will get an approximate answer. In this case, it's going to underestimate the deflection. Ideally, you want to guess that matches all of the boundary conditions. The kinematic ones are the ones that are essential. If you need to have those to be satisfied by your guess function. If you only have those, you'll come close. If you have all 4 of them, you can converge to the correct answer. This method, this Ritz method for approximating solutions is incredibly powerful. I will repeat what I said at the beginning. It works on static problems, dynamic problems. If you want to find the vibrational frequencies of a plate, it works for buckling problems. So instabilities in which there are multiple modes of instability that you're choosing between, not something like a beam, maybe something like a plate. The Ritz method is really powerful for solving a whole class of these problems: linear, nonlinear elasticity. It's a remarkably powerful problem. And it really comes down to knowing the form of the total potential energy and then making a guess and being aware of what boundary conditions it satisfies. That's all I have for you today. There's homework due tomorrow. There's a new homework due next Wednesday evening. And I might see some of you in office hours later. Take care.